When analyzing a circuit, it's helpful to think in terms of branches, loops, and nodes. A branch consists of one or more elements in uninterrupted series. For example, this single resistor is a branch. However, the combination of this battery and this resistor does not make a branch. That is because at this point on the circuit, you can go one of two ways, either to this resistor or to this battery. If, when traveling across a circuit, you reach a point where you can go in one of two or more different directions, the branch you are on has ended. So, this battery and this resistor are on the same branch because you can travel from the battery to the resistor without facing a point where you can split in two different directions. To make this a little clearer, we can re-represent this circuit by writing the 1-volt battery and 10-ohm branch in this manner. With some observation, you can see that these two circuits are identical. And you can see that it is an uninterrupted path or uninterrupted series from this battery to this resistor. Please note that I am representing the resistors simply as their ohm value. I will do this throughout most of my lectures. Another helpful fact we get from looking at this diagram is that these three branches, 1, 2, 3, are in parallel. Branches are in parallel if their starting and ending points are the same. That is, if you went to the starting point of any branch, and you tried to go to the ending point of that branch, you could go upon multiple paths and always end up at the same place. If I wanted to go from the starting point of this branch to the ending point of that branch, I could go across that branch, or I could go across this branch or this branch. However, this branch and this branch are not in parallel. Starting from this point, I could go down to the bottom point here just by going through the 3-ohm resistor, but I couldn't go to this bottom point just by going through the 2-ohm resistor. I have to go to the 4-ohm resistor as well, and then I could go in either the 2-ohm direction or the 1-ohm direction. Basically, the two branches have to start in the same place and end in the same place to be parallel. That means that the 2-ohm resistor and the 1-ohm resistor are in parallel here. It also says something about something we could call super branches. An electron which wished to travel from this point to this point could either travel upon this path or upon a path that goes through the 4-ohm resistor and either this 2-ohm resistor or this 1-ohm resistor. So in a sense, we could describe this entire section of the circuit here as a branch. This will become especially relevant in a moment. Let's go back to this circuit and consider an electron that starts at the bottom of this battery. We remember that the battery pushes it up to the positive end of the battery and gives it 9 volts of potential. As the electron moves, let's say it passes through this resistor. Then it returns back to the bottom of the battery. Because of the need for electrons to be distributed evenly, and the resistance of the resistor keeping the electrons from moving, the electrons traveling through this resistor move at a certain definite speed, and all of their voltage gets used up. If they retained some extra energy for movement and then the battery gave them an extra 9 volts, they would be traveling even faster when they go through the resistor again, which would violate the idea that they're all traveling at the same speed along this branch. So 2 useful things to know. First of all, in this branch, the current is constant the entire way through. Secondly, all of the voltage gained by an electron in this branch needs to be used up in this branch so that the electron can go back to the beginning of the battery. So if an electron gains 9 volts traveling up across this battery, then it will lose 9 volts traveling down across this resistor. If this is a ground, or 0 volts, then this point is 9 volts, because the battery provides 9 volts. And if this point is 9 volts, then this point must be 0 volts because this resistor takes away 9 volts. If you were to walk up the circuit along this direction, you would see the voltage rise from 0 volts to 9 volts. The same thing would occur if you walked up this direction. That means that the voltage rise is the same across any 2 parallel branches. So is the voltage drop. If we started from this point and went down, of course we would have 0 volts as opposed to 9 volts. And if we started from this point and went down, again we would go from 9 volts to 0 volts. The voltage across parallel branches is the same. Again, a particle traveling, instead of over the 3 resistor, over the 1 volt battery and the 10 ohm resistor, still has to end at the bottom of this battery, so it ultimately has to lose 9 volts. So it gains 1 volt at this battery, and then loses 10 volts at this resistor. So ultimately, there's still a 9 volt drop across this branch. The fact that an electron is supposed to lose 9 volts across this branch helps us analyze what the voltage drop across this resistor is. We know that because it gains an extra volt when it goes across this battery, it has to lose that extra volt and all 9 volts when it goes across this resistor. So this resistor must experience a 10 volt drop as opposed to just a 9 volt drop like this resistor does. So let's return to that thing I said about the super branch. Let us suppose that an electron loses 5 volts when it travels across this resistor. That means that it must also lose 5 volts when it travels across this entire area. It may either lose 5 volts by traveling down the 4 ohm resistor and then the 2 ohm resistor, or the 4 ohm resistor and the 1 ohm resistor, but no matter what it does, it has to lose 5 volts. So maybe we could remodel this branch as just one single resistor that would cause an electron to lose 5 volts. And we'll eventually use that property more in circuit analysis.